Welcome to the lecture on hashing and digital signatures, two widely used techniques in cybersecurity. Let's start with hashing. So what happens in hashing is that you provide an input or a document to a one-way hashing function, which basically generates a fixed-sized message digest or a summary as the output. Now the key point to understand here is that you can provide a document of any size. It can be small, it can be big, but the output size or the message digest size would remain fixed. Another important point to understand about hashing functions is that they're one way. So if I give you the message digest, it is impossible for you to reverse the hash function and obtain the original document. In fact, this property of hash functions is of critical importance. It should be impossible to recover the original data or the original file by reversing the hash function. Another important point to understand about hashing is that if you provide two different input documents, it should lead to different hashes, which means that different inputs should lead to different outputs. And if this does not happen, for example, if you provide two different types of documents or input data and they lead to the same message digest, then we say that we have a collision. And hashing functions which cause collisions are considered poor. A major application of hashing is in ensuring file integrity. Let's see how this works. So let's say you have a source with a file. So what the source does is that it passes the file through a one-way hash function and calculates the hash and stores it along with the file. Now a user goes ahead and downloads the file and its corresponding hash. And now the user recalculates the hash of the downloaded file independently. In the next step, the user compares the downloaded hash with the hash that it has calculated independently. The two hashes must match. If the two don't match, then it means that the file has been compromised and the integrity can no longer be trusted. Another major use of hashing is in digital signatures. So just like their counterparts, digital signatures provide authenticity of a message, which means that if someone has digitally signed a document or data, then they're giving the assurance that that data or file is in fact coming from them. Let's see how digital signatures actually work and how they leverage hashing. So there is a source with a file. What the source does is that it calculates the hash of that file, and then the source signs that hash using his private key. And then this signed hash is stored along with the file. Now please note that this hash is not visible as plain text. It has been encrypted or signed with the private key of the user. And we call it a digital signature because only the source has access to the private key and nobody else in the world can encrypt the data using source's private key. So now the user downloads the file as well as the signed hash, and the user recalculates the hash of the downloaded file independently. Now the user also has access to the public key of the source, and he decrypts the signed hash using the public key. So the only way this hash could be decrypted was if this was signed by the private key of the source, and that's why we used the public key to decrypt it and it worked. So this is the basic principle of public key cryptography. Anything which is encrypted with private key can only be decrypted with the public key, and vice versa. So now the user has obtained the unencrypted or the plain text hash, and he has also recalculated the hash on his own. So as a last step, the user compares the two hashes, and if the two match, then it means the digital signature is valid and this file actually came from the sender. However, if there is any difference, then this means either the file has changed or somebody has tried to modify the contents of the signed hash. In either case, the authenticity is violated. And we can be sure that this was encrypted by the source because only private key can be used to encrypt data which is subsequently decrypted by the public key. So just like their counterparts, digital signatures provide authenticity. What it means is that if someone digitally signs a document or data, then they're giving assurance that this data or this file is in fact coming from them. A digital signature is always done using the private key, and the corresponding public key is distributed to thousands of users. So we are again leveraging the concepts of public key cryptography, in which you sign using your private key or you encrypt using your private key, and then you distribute your public key to the public at large, and they can decrypt your message using your public key. Confidentiality can additionally be added by encrypting the entire file using the private key in addition to the hash. Some popular hashing solutions include MD5, the message digest algorithm, which always creates 128-bit fixed-sized output hashes regardless of the input. However, in some instances, MD5 has been shown to suffer from collisions. What this means is that for two different inputs, it generates the same message digest or the hash. We also have SHA-2, the secure hash algorithm. Now, SHA-1 is known to be weak as is no longer used. However, for SHA-2, we have different outputs available. We have SHA-224, 256, 384, and 5112. So these numbers represent the size of the hashed output. This concludes our lecture. I'll see you in the next one.